Have you ever wondered what it's really like to walk through the Boeing 737 MAX 10? Not from a passenger seat, but from the perspective of someone who sees every inch of the aircraft like a pilot or engineer would. If you're someone who finds comfort in the hum of jet engines, who notices the shape of a winglet before even boarding, or who follows aviation news like others follow sports, then this walkthrough was made for you. Today, we're diving into the Boeing 737 MAX 10. Not just with surface-level facts, but through a realistic AI-powered showcase that replicates the aircraft in stunning accuracy. From nose to tail, cockpit to cabin, everything has been recreated with precision, giving you a near-real experience, even from your screen. And if you stay till the end, we'll reveal something special: how the latest advancements in AI modeling are not only changing how we simulate aircraft, but also how we feel about them. You'll see how realism affects our brain, and why it makes experiences like this strangely satisfying. But before we get to that, let's understand what makes the 737 MAX 10 such a big deal in the world of commercial aviation. The Boeing 737 MAX 10 is the largest and most advanced version of the 737 family to date. With a longer fuselage than the MAX 8 and MAX 9, it can carry up to 230 passengers. That's more than any 737 variant in history. At first glance, it might look similar to its predecessors, but small changes make a big difference. In aviation, every inch, every angle, every system, it all adds up. And the MAX 10 was designed to compete head-on with aircraft like the Airbus A321neo, especially on high-density short to medium-haul routes. What's fascinating is how Boeing managed to stretch the aircraft without completely redesigning the structure. The MAX 10 has a 168-meter longer fuselage than the MAX 9. But to accommodate that, they had to innovate, particularly with a new semi-levered landing gear system that allows for a higher rotation angle during takeoff without changing the basic height of the airframe. This kind of design challenge is what aviation lovers appreciate, solving complex problems with elegant engineering. It's not just about more seats, it's about doing more with the same platform. And that's part of the genius behind the MAX family. Boeing wanted all MAX variants to share a common type rating, meaning pilots trained on one model can fly any MAX version with minimal additional instruction. From a human psychology standpoint, this is powerful. It's about efficiency, trust, and predictability, traits our brains are hardwired to respect, especially in high-risk environments like aviation. Now, let's talk about this walkthrough. What makes it different from the usual flyover footage or cabin tours? This isn't a marketing video. It's a realistic AI showcase, meaning every detail, from surface textures to cockpit buttons, is rendered using advanced simulation tools that mimic not just visuals but behavior. The way shadows fall across the fuselage, how the lighting changes in the cockpit, the subtle movement of landing gear, it's all modeled to reflect the real aircraft as closely as possible. And here's where it gets interesting from a psychological angle. Studies in neuroscience show that the brain processes high-fidelity simulations similarly to real experiences. That's why realism triggers immersion. For aviation enthusiasts, the joy isn't just in flying, it's in understanding, in observing, in experiencing the aircraft as a system of interconnected parts. The satisfaction you feel when watching a perfectly rendered cockpit panel isn't accidental. It taps into what psychologists call the mastery loop. A mental feedback cycle triggered when we recognize structure, logic, and purpose. The more detailed and accurate the experience, the more your brain rewards you with a sense of control and understanding. That's why this video goes deep, not for the sake of complexity, but for the sake of authenticity. Because we know that aviation fans don't want fluff. They want facts. They want fidelity. They want to see the aircraft as it truly is. Not just as a vehicle, but as a machine built to fly perfectly at 35,000 feet. And in the case of the 737 MAX 10, that's exactly what we're showing. So whether you're a future pilot, a simulation enthusiast, an aerospace engineer, or simply someone who loves the sound of a CFM engine spool up, this walkthrough was crafted with you in mind. As we begin this tour, remember this: every part of this aircraft has a purpose. Every line, every shape, every system tells a story of function, safety, and innovation. That's what makes aviation beautiful. And with AI, we can now appreciate that beauty in more detail than ever before. Stay with us, because in the next section, we'll begin with the external design of the 737 MAX 10. From its signature split winglets to the changes in landing gear that make this jet stand apart. The realism here might just surprise you. We begin at the nose, the signature profile of the Boeing 737 family. With the MAX 10, that iconic rounded front remains largely unchanged, preserving the aerodynamic balance Boeing has refined for decades. But what lies behind it has been thoughtfully stretched, reshaped, and optimized. The MAX 10's fuselage measures just over 143 feet, making it the longest 737 ever built. This extension isn't just about adding seats. It's about maximizing efficiency while staying within strict airport compatibility. Longer fuselage means higher passenger count, yes, but it also demands changes in balance, weight distribution, and takeoff dynamics. That's why Boeing introduced a semi-levered main landing gear system in the MAX 10. Unlike previous versions, this gear design allows for a greater pitch angle during takeoff without risking a tail strike. It uses a kind of mechanical arm that leans the aircraft back slightly as it rotates. This is critical for an airplane that's longer and sits low to the ground. It's a subtle change, but one that speaks to the precision involved in modern aircraft design. For aviation lovers, this kind of detail hits home, where every component isn't just built, but engineered for harmony. Moving along the fuselage, notice how the AI model captures even the smallest details: panel lines, static ports, antenna placements. These aren't just cosmetic. Each of these elements has a function. Some are pressure sensors. Some are for data transmission. Others, like vortex generators, are designed to improve airflow over specific surfaces. The realism in this showcase allows you to see these things clearly, without visual clutter. As we reach the wing root, the transition from body to wing is smooth, shaped not just for looks, but for reducing drag. The 737 MAX series features advanced technology winglets, also known as split scimitar winglets. These are double-blade extensions, one curves upward, the other downward. This design improves fuel efficiency by reducing wingtip vortices, those circular air currents that form as a result of pressure differences between the top and bottom of the wing. By controlling these vortices, the aircraft reduces induced drag, resulting in fuel savings of up to 1.8% compared to traditional winglets. To the human eye, these winglets look elegant. To the aviation brain, they signal refinement. Our minds respond positively to symmetry and curvature, especially when we understand their purpose. It's the intersection of beauty and function, a powerful cognitive trigger for enthusiasts. Under the wing, the engines demand attention. The 737 MAX 10 is powered by CFM International LEAP 1 billion engines, the same used across the MAX family. These engines are larger, cleaner, and quieter than those on older 737 models. The LEAP 1 billion has a 69-inch fan diameter, requiring it to be mounted slightly forward and higher on the wing than previous generations. This shift improves ground clearance and airflow. It's one of the key visual identifiers of the MAX, and one that was only possible thanks to modern engine materials and digital design tools. These engines feature composite fan blades, 3D printed components, and advanced combustion systems that reduce NOx emissions by up to 50%. That's not just good engineering, it's a response to real-world aviation demands: lower fuel burn, less noise, and smaller environmental footprint. In this AI showcase, you can observe the engine nacelle contours, the pylon attachment, and the blade geometry with surprising clarity. This level of detail creates immersion, but it also feeds our human desire for understanding. When we see how something works, we form a deeper appreciation for why it was made that way. As your view moves toward the tail, the stability surfaces come into focus. The horizontal stabilizers and vertical fin look familiar, but they've been tweaked for performance. Control surfaces like the rudder and elevators are rendered with realistic hinge lines and surface textures. Again, small details, but psychologically satisfying. Aircraft lovers are often drawn to order, control, and mechanical logic. The layout of an aircraft's surfaces, flaps, slats, spoilers, speak a language of purpose. And that's why these AI recreations feel so real. They let you follow that logic with your eyes, almost like reading a map of aerodynamic intelligence. The lighting systems, navigation, strobe, and taxi lights, are placed in standard positions, but the simulation highlights how these interact with the environment. Light reflection on the fuselage, shadow diffusion across curved surfaces, and realistic lens bloom create depth. This is not visual trickery. It's a reflection of how our brains process realism. From a psychology perspective, high-fidelity visuals stimulate what's known as perceptual fluency, the ease with which information is processed. When something looks accurate, we trust it more. That trust creates engagement, and that engagement turns into fascination. And that's what this section delivers. A chance not just to see the aircraft, but to understand it through design, to feel the harmony between structure and purpose, to recognize that what you're looking at isn't just metal and composites, but the result of decades of innovation, safety, evolution, and engineering discipline. Every part of the MAX 10's exterior tells a story. A longer body, stronger gear, efficient engines, and drag-reducing winglets. Each part tuned for performance in today's competitive skies. And when AI models are able to recreate all of this with near-perfect accuracy, what you get isn't just a visual walkthrough, it's a real mental experience. One that feels almost tactile, almost tangible. And for those who love aircraft, that's the kind of realism that keeps us coming back. Stepping into the flight deck of the Boeing 737 MAX 10 is like entering the brain of the aircraft. It's here where mechanical design meets human decision-making, and it's where the connection between man and machine is at its most focused. The layout of the MAX 10 cockpit reflects Boeing's long-standing philosophy: familiarity, clarity, and control. For pilots, these three traits are critical. The MAX family was built with a key requirement: to maintain a common type rating with previous 737 variants. That means a pilot trained to fly the 737-800 can transition to the MAX with minimal retraining. From an engineering perspective, this saves airlines time and money. From a psychological angle, it reduces cognitive stress. Humans perform best in environments where they can predict outcomes. Familiar interfaces, repeated procedures, and consistent systems help build trust. And in aviation, trust is everything. At first glance, the cockpit looks similar to the next-generation ING series. But a closer look reveals important upgrades. The analog dials have been largely replaced with large-format LCD displays, part of the Rockwell Collins avionics suite. These displays are fully digital, fully configurable, and offer better visibility in all lighting conditions. Pilots can customize how data is shown, from engine readouts to navigation maps, system status to weather overlays. This modularity isn't just a technological improvement, it taps into how the human brain processes information. When data is grouped by relevance, decision-making becomes faster and more accurate. It's called cognitive chunking, and it's a key factor in reducing pilot workload during high-stress phases like takeoff and landing. The Flight Management Computer, or FMC, is still front and center, a familiar keypad interface that controls routing, performance, fuel planning, and more. Despite the rise of touchscreen systems in other aircraft, Boeing chose to retain tactile buttons. The reason is subtle but important: tactile memory. Pilots often operate these systems without looking directly at them. Muscle memory reduces errors. Tactile input gives physical feedback. In a high-workload cockpit, these small features make a big difference. Above the FMC, the Mode Control Panel MCP controls autopilot modes, heading, altitude, speed, and vertical navigation. The layout is clean and intuitive. Switches are deliberately placed to reflect frequency of use. The knobs have specific resistance, not too stiff, not too loose, designed to prevent accidental changes. This kind of sensory calibration may seem minor, but it plays directly into human performance psychology. The brain uses physical feedback to confirm intent. That's why professional tools in aviation, medicine, engineering are always designed with precision tactile responses. It's not just design, it's human-centered engineering. One of the most visually striking features is the optional head-up display HUD. This transparent screen folds down in front of the captain's eyes and projects critical flight data directly into the pilot's line of sight. Altitude, speed, pitch, flight path vector, all shown without needing to glance down. The HUD is more than a futuristic overlay. It allows pilots to keep their eyes outside the cockpit, improving situational awareness during approaches, low-visibility landings, and terrain-rich environments. The psychological benefit here is simple. Reduced eye movement means faster reaction times, and faster reactions mean safer outcomes. Now let's talk about the thrust levers and control columns, the true physical connection between pilot and aircraft. Unlike fly-by-wire systems found in aircraft like the Airbus A320, the 737 MAX retains mechanical linkage in the yokes. When the captain turns left, the first officer's yoke turns in unison. This tactile feedback reinforces teamwork and shared situational awareness. For many pilots, this is one of the reasons they prefer Boeing's traditional controls. There's a deeper connection to the aircraft's movement, a sense of feeling the plane through control forces. This is where passion and psychology overlap. The idea that flying isn't just monitoring systems, but actively participating in the flow of flight. The rudder pedals, trim wheels, speed brake lever, and flap lever, all modeled realistically in this AI showcase, give you a close-up view of the systems pilots interact with hundreds of times per flight. From controlling descent rates to preparing for landing configuration, every motion follows standard operating procedure. But behind that procedure is habit, discipline, and repetition, all rooted in how the brain learns complex motor skills over time. Lighting plays a key role in cockpit design too. Overhead panels, circuit breakers, lighting knobs, annunciator panels all feature adjustable backlighting. Pilots need to balance visibility with night adaptation, especially during dusk and dawn operations. The AI model replicates these subtle lighting shifts, helping viewers experience the spatial awareness that real pilots develop after hours in the seat. The overhead panel itself holds systems management controls, electrical, hydraulic, pneumatic, air conditioning, and anti-ice functions. Every switch follows a logic path. Most up for on, most down for off. This design symmetry is no accident. It helps reduce confusion and aids muscle memory. Again, it's about reducing mental friction, a key part of cockpit ergonomics. Sound also matters. While this is a visual walkthrough, it's worth noting that every system has a sound signature. The click of a switch, the trim wheel spinning, the alert chimes. These audio cues are as important as visual ones. They create a multisensory environment that pilots learn to interpret intuitively. Together, these elements form an ecosystem, a workspace designed not only for function but for human performance. And that's what makes the 737 MAX 10 cockpit special. It doesn't overwhelm. It supports. It provides clarity and complexity. For aviation lovers, seeing this flight deck in realistic detail creates a kind of immersion that few other environments can match. It's not just about flying, it's about being part of a system that's built for precision, discipline, and flow. When realism is this high, your brain responds with focus. Your curiosity sharpens, and you don't just observe the aircraft, you start to think like a pilot. Leaving the flight deck, the transition into the passenger cabin marks a shift from precision controls to human comfort. Yet, just like the cockpit, the cabin of the Boeing 737 MAX 10 is a product of years of design thinking, engineering, and behavioral insight. Every surface, light, and seat is part of a system intended to guide how passengers feel from boarding to landing. The first thing that stands out is space, not in terms of width, but perception. Boeing uses what it calls the sky interior, a modern cabin design philosophy introduced with the 737 series and carried through to the MAX 10. The overhead bins are sculpted upwards, with soft edges and curved lines that trick the brain into perceiving more headroom. This is a deliberate visual effect based on spatial psychology. When lines curve upward, our brains interpret that as openness. Passengers feel less confined, even though the actual dimensions haven't changed dramatically. The LED lighting plays a major role too. Cool blues during boarding suggest calm. Warm ambers before takeoff signal readiness. Soft purples during cruise simulate natural light and reduce fatigue. These light settings are not aesthetic choices, they're grounded in circadian rhythm research. Human psychology responds strongly to lighting cues, especially in enclosed spaces like aircraft cabins. The right lighting can reduce stress and create a sense of time and flow, even during long flights. Walking down the aisle, the seat configuration is typically 3-3, a standard for narrow-body aircraft. But what matters here is the detail. The seatback design, tray tables, legroom, all have been refined over generations. In the MAX 10, many carriers choose slimline seats with optimized recline angles and adjustable headrests. While seat pitch can vary by airline, the structure itself promotes upright posture and efficient use of space. Materials also influence perception. Seat fabrics in newer configurations tend to be darker, not just for maintenance, but to reduce visual clutter. Clean lines, matte textures, and minimalistic color palettes create a sense of order, which reduces cognitive fatigue. Our brains prefer clean environments. In aviation, that translates into seats and surfaces that don't overstimulate. Cabin sound is another hidden design feature. The LEAP 1 billion engines, mounted farther forward and tuned for quiet operation, significantly reduce cabin noise compared to earlier generations. Quieter cabins improve the passenger experience, not just through comfort, but by reducing cortisol levels, the body's stress hormone. Studies have shown that lower ambient noise helps passengers relax, especially during climb and descent when ear pressure and motion sensitivity are at their peak. As you move through the aircraft, door operation, exit rows, and lavatory access follow a strict logic. These aren't just regulatory requirements. They're designed for flow, a term often used in both psychology and architecture. People move more calmly and efficiently in spaces that feel predictable. The MAX 10 preserves that consistency. Exit signs are visible from every seat. Path lighting along the floor ensures orientation in darkness. These features reinforce safety not just visually, but subconsciously. At the rear galley, utility takes precedence. Galley carts, fold-down jump seats for crew, waste compartments, and trolleys are arranged with purpose. In the AI showcase, the texture of these components, the metallic surfaces, and the lighting reflections are all modeled accurately, reminding us that even the most functional areas contribute to the aircraft's overall character. Back toward the forward galley, you pass the premium seating zones, sometimes business class, sometimes extra legroom economy. These zones are separated by small cabin dividers or soft barriers. The separation is both physical and psychological. Passengers feel different levels of status and space, and that feeling affects their perception of comfort. Even when seats are only inches apart in pitch, the placement and layout can shape how passengers interpret value. Overhead panels above each row include individual reading lights, air vents, and attendant call buttons. The interface is tactile, simple, and unchanged for years. Another example of behavioral consistency. When passengers know where things are, they feel in control. And when they feel in control, they're more relaxed. The AI's recreation of these panels captures their precise placement and proportions, reinforcing how even small features carry large functional value. The windows on the MAX 10 maintain the classic 737 shape, but benefit from improved insulation and better placement alignment with seat rows. The spacing ensures that more passengers get an unobstructed outside view, and that view plays an underestimated role. Looking out over the wing or into the clouds provides a grounding experience. Psychologically, it reduces spatial disorientation and contributes to emotional calm, especially during turbulence or long cruise segments. Above all, what this walkthrough showcases is the idea that modern aircraft are not just machines, they're experiences. Every touchpoint in the MAX 10's cabin has been refined to align with how people think, move, and react. From visual layout to sound, from lighting temperature to material design, it's a carefully tuned environment built for both function and feeling. The realism of this AI model allows aviation lovers to see that clearly. It lets you step into the experience without stepping onto the aircraft. For some, it's preparation for a future flight. For others, it's appreciation for an engineering marvel. But for many, it's a moment of connection with the aircraft, with the design, and with the dream of flight itself. What's most remarkable is how realism bridges the gap between curiosity and satisfaction. The sharper the detail, the deeper the focus. And the deeper the focus, the more the brain rewards you. This is why true-to-life simulations feel rewarding. They align with our natural desire to understand complex systems in a controlled, safe way. The Boeing 737 MAX 10, recreated here with high-fidelity AI, becomes more than a plane. It becomes a visual map of everything aviation enthusiasts admire: innovation, balance, purpose, and progress. And when that map is clear, the journey becomes something more than just transportation.